Hi, my name is Smitha. I'm a PhD student at Berkeley, and I'm going to be telling you about our work on human model misspecification in objective learning. So first, what is objective learning? Well, most of the problems that we focus on in AI and machine learning rely on objective specification. We work on problems where we assume a given objective or reward function that's been specified by the designer of the system. But in many cases, it's a non-trivial task to figure out what the correct objective should be in the first place. Like, for example, consider, the self-driving car. What is the correct objective for a self-driving car? I don't think I would be able to hand specify that objective. And so increasingly, people have turned towards objective learning instead, which is the problem of trying to learn what the objective is from human behavior. So for example, in the self-driving car setting, you might imagine getting demonstrations of humans driving and then inferring what the underlying objective is from that behavior. In order to do objective learning, there's one crucial thing you need, which is a link between the observed human behavior and the underlying objective or reward function. And this is where the human model comes in. So the basic idea behind most objective learning methods is to assume that the human is approximately rational with respect to the objective. And this is what provides a link between human behavior and the objective. So for example, looking at the demonstration setting again, we might assume that the probability that the human gives a demonstration psi is proportional to, say, the exponential of the reward of that demonstration. So a human is more likely to pick a demonstration the higher the reward of that demonstration. And then given this sort of forward model of how the human will behave, we can then infer what the reward is by essentially inverting this model and doing inference. But you might be a little skeptical about this assumption, this rationality assumption, because we know in many cases humans deviate from this. And one case in which humans deviate from this was shown in empirical experiments done by Ho et al. In 2016. So they gave mechanical Turkers grid worlds with 3 types of colors on them. Each color could be either safe, positive reward, or dangerous, negative reward. And in one condition, which I'll call the literal condition, they asked people to optimize for the number of points that they received. And in this case, humans basically follow this approximate rationality assumption pretty well. But in another case, they did something slightly different. They told people that their demonstrations would be used for objective learning. So in particular, they said that after they demonstrated, a partner would receive the demonstration and then try to infer what the reward is. And here, people actually did something different. In particular, they picked more communicative demonstrations, where they made sure to go through all the safe colors, and in some cases they even looped over the safe colors multiple times to emphasize that those colors were safe. So in this condition, which I'll call the pedagogic condition, what this reveals is that in collaborative environments, when humans know that their behavior is going to be used for objective learning, they often try to teach the objective rather than optimize for the objective directly. Recent work has proposed to try to increase the accuracy of objective learning by directly modeling the human as pedagogic in these collaborative environments. But the question that we want to ask in our work is, which model is more robust? Because one of the key directions in trying to do objective learning in the first place is that objective specification is very brittle. But if the human model needed for objective learning also turns out to be brittle, then this undermines some of the original motivation for trying to do objective learning in the first place. And our key takeaway in our work is that the literal assumption, the standard rationality assumption, is actually more robust than the pedagogic assumption. And we'll argue for this in 2 ways. First, we'll argue for it theoretically, where I'll formalize what I mean by literal and pedagogic, and then we'll argue for it empirically with real human data. So first, let's look at it theoretically. In most objective learning, because the human is assumed to be rational with respect to the objective, we can't capture the sort of collaborative pedagogic behavior that we want to look into. And so first, what we're going to have to do is generalize objective learning to the collaborative setting. And the way we do this is by casting objective learning as a common payoff game. a game in which the human and the system, which I'll just call the robot, have the same payoff, U of H, the human policy, and R, the robot policy. This is very closely related to the cooperative inverse reinforcement learning framework and the cooperative inference framework, which I've cited on the slide. So to understand how this generalizes objective learning, let's look again at the demonstration setting, the inverse reinforcement learning setting. In this case, the common payoff game would be one in which the human knows the reward R, and her action consists of giving a demonstration D. The robot observes a demonstration D, but does not know the true reward R, and has to output an estimate of the reward R hat. Then their joint payoff is simply the accuracy of reward inference. And so it's clear that the robot is incentivized to do the best inference it can about the reward, but it's also clear now that the human is also incentivized to pick the most communicative demonstrations that they can. So now, given this setup of the common payoff game, it becomes very natural as to how you formalize literal and pedagogic. We can formalize these as recursive policies in the common payoff game. So we'll start with a literal human policy H0, and on the next slide I'll give an example of what this could be. And then we can define a literal robot policy as the policy R0 that does a best response to H0. Then we can define the pedagogic human policy as the policy that is a best response to the literal robot policy. And the reason we call this the pedagogic policy is because now the human is optimizing to try to essentially teach this literal robot policy. And we also technically don't need a best response, we just need H1 to be better than H0. And I just mentioned this because it might be a strong assumption for humans. And then we can also consider a pedagogic robot, which now assumes that the human is trying to teach it and does a best response to H1. So to ground this out in a concrete example, let's return to that inverse reinforcement learning example and see what happens. So we can start off with the literal human policy being just that standard rationality assumption where you're more likely to give demonstrations based on the reward of that demonstration. Then what the literal robot policy will end up being is Bayesian inference given the literal human policy. Then the pedagogic human picks demonstrations in proportion to how much they cause the literal robot to infer the right reward. And then the pedagogic robot does Bayesian inference, assuming the pedagogic human policy. So now we can ask, which type of misspecification is worse? Is it worse on the left-hand side to assume that the human is pedagogic when they're not? Or is it worse on the right-hand side to assume that the human is literal when they're not? A priori, we might not be sure because in both cases the robot has a wrong model of the human. But because of the recursive structure of these policies, it becomes clear that the left-hand side is worse. And this is very simple to see. So we can just start off with the joint payoff of the literal human and pedagogic robot. And this must be worse than the joint payoff of the literal human and literal robot because the literal robot is a best response to the literal human. This must then be worse than the joint payoff of the pedagogic human and literal robot because the pedagogic human is a best response to the literal robot. And then this must be worse than the joint payoff of the pedagogic human and pedagogic robot because the pedagogic robot is a best response to the pedagogic human. So in just one line, we can see that we can order all possible pairs of literal and pedagogic robot and human policies. And in particular, one thing to note is that indeed, if we know the human is pedagogic, then the best possible payoff we can get is by modeling the human as being pedagogic. However, if we aren't sure, then it is worse to incorrectly assume pedagogic than incorrectly assuming literal. So the literal assumption is a more robust assumption in that sense. Now, everything I've shown you so far still makes the idealized assumption that the human is either literal or pedagogic. But of course, real humans will deviate from both our literal model and our pedagogic model. So next, what we wanted to do is test how this held out with real human data. And the way we did this is by revisiting the experiments that Ho et al. Did in 2016. What Ho et al. Focused on in their experiments was the human side to these. In particular, they came up with a literal and pedagogic model, very similar to what I've described to you thus far. and they found that the literal model was a better fit to humans in their literal condition, and that the pedagogic model was a better fit to humans in their pedagogic condition. What we want to focus on now is the robot side of the equation. What should the robot assume about the human? And in particular, we are wondering, does this ordering hold with real human data? And the reason, why this is interesting is because real humans could potentially deviate from both our model of the literal human as well as our model of the pedagogic human. So first, let's just do a quick sanity check. We took the models that Ho et al. Fit and simulated data from them. And since we're just simulating this data, we surely expect to get the ordering that we saw before. And indeed, on this plot, on the x-axis, you'll see the pairs of robots and humans, and on the y-axis is the accuracy of the inferred reward. And indeed, we saw exactly this ordering. And when we look at the misspecified pairs, it is worse to incorrectly assume pedagogy than incorrectly assuming literal. Now, when we go to real human data, again, we find that it's worse to incorrectly assume the human is pedagogic than incorrectly assuming the human is literal. But we also found another thing that was somewhat surprising, which is that even for humans in the pedagogic condition, it didn't really help to model that pedagogy. And in fact, it made things slightly worse. So why could that be the case? I mean, these humans are in this pedagogic condition where they're supposedly teaching, but somehow it doesn't help us to try to use that model of them. So a naive immediate answer is, well, clearly the pedagogic model is misspecified. And this plot is going to try to explain why that answer is naive. So on the x-axis here, I have the condition that the human was in the experiment. And on the y-axis is going to be the mean negative log likelihood of each of the models. So in the literal condition, the literal model is a better fit than the pedagogic model. In the pedagogic condition, the pedagogic model is a better fit than the literal model. So the reason this answer doesn't really work as an explanation is that, yes, the pedagogic model is misspecified, but the literal model is more misspecified than the pedagogic model. And so it doesn't provide a satisfying explanation for why the robot does worse using the pedagogic model. And another thing I want to just mention is that sort of naive fixes of like trying to estimate the amount of pedagogy instead of just doing this very binary literal or pedagogic assumption also doesn't help. That's in the paper, but I can't talk about it right now because of time. What we really ended up coming to and realizing was that the literal model was more inferentially robust, which was different from it being good as a predictive model of the human. And just to make concrete what I mean by that, let's assume we have a data set D of reward and demonstration pairs, and then we fit a model M that models the conditional probability of the demonstration D given the reward R. This is essentially exactly what happened in this Ho et al. Experiment. Then I can define the predictive likelihood of that model to be the likelihood of the demonstrations under the model. I can also define what I'll call the inferential likelihood, which is the likelihood of the rewards in the data set after I apply Bayes' rule to this forward model. And the key thing to note here is that a higher predictive likelihood does not necessarily mean a higher inferential likelihood. So in other words, these human models are usually evaluated on prediction, but a better predictive model does not necessarily mean better inference. And this was a subtlety that was initially very counterintuitive to us. So in conclusion, I've talked to you about whether or not we should, use a literal model or a pedagogic model, and I hope by now I've convinced you that the pedagogic model is a quite brittle assumption. But more generally, I hope to convince you of the need for looking into the robustness properties of these human models, because humans will always deviate from the models we have in some way, and so it's crucial to make sure that the models we use within our algorithms are robust to these deviations. Thank you.